Our next problem in our 4.3 series, this is video D, is a can of soup must contain 36 cubic inches of soup. What are the optimal dimensions so that the aluminum top, sides, and bottom are minimized? And so we have our problem, and the first thing we're going to have to do is to try to make a picture, and we certainly know what a soup can looks like. I guess I should have written that the thing is cylindrical, but we're going to have a couple things here. I think R is an important value. I think H is an important value. And I'm not just going to draw this one. I'm also going to say that this is what the can looks like, but we're also concerned what the top, sides, and the bottom look like. So if I take a can opener and I cut off the top, we're going to have a circle of radius R. We'll also have the bottom, which has a circle of radius R. And then we'll have the sides. And if I was to cut, say, a slit down the side and unroll the can, we would have a rectangle, and this value would be H. That's the side of our can. This right here, we can see that it wraps all the way around the circle, so that's our perimeter, 2 pi r. So we've taken care of our diagrams, and now what are we trying to optimize here? And we're trying to optimize the dimensions so that the aluminum is minimized. That's a surface area idea. And the units are going to be inches square. And so when we look at our can, we're going to have a circle, pi r squared, but I'm going to have two of them, so I'll multiply that by 2. I'm going to have this rectangle, which has an area of base times height, 2 pi r h. Okay, we're in trouble. And the trouble that we're in is that we have more than one variable going for us. And so we're going to need to make our constraint equation. So where is that going to come from? Well, it's the only other number that we see here, that 36 cubic inches. So that's a volume idea, and the volume of any rectangular solid is the area of the base multiplied by the height. And now that we have our constraint equation, we're going to have to solve for one of these variables and then substitute in to our surface area. So if we keep going with our guide, this was step 3 right here. We made our constraint. Step 4, not always necessary, but 2 variables it is. And so now we're going to substitute in. And I'm going to solve this for one of these 2 variables before I sub. And I think the only thing to solve for is H. So H equals 36 over pi r squared. And now I can plug that into my surface area. And my surface area is only going to be a function of r. All the h's will be gone. 2 pi r squared. This term came along for the ride. Then we'll have 2 pi r times 36 over pi r squared. I love this formula. This is a great formula, but I do want to do a little bit of housework before we go. Surface area as a function of r will be 2 pi r squared. And now we can see the 2 and the 36. That'll give us a glorious 72. The pi's will murder. The r's will murder. We'll just have this over r, which I'm probably just going to think of as 72 times r to the negative first. So there we have it. Now it's time to take our derivative. And so the derivative of the surface area with respect to r is 4 pi r minus 72 r to the negative second. We set our derivative equal to 0 and we begin to solve. 4 pi r minus, and I'm going to write it as 72 over r squared. And that should give us some inspirato that what I'm going to do is I'm going to multiply by r squared all the way through to get rid of this terrible fraction. So we'll have 0 is equal to 4 pi r cubed minus 72. And solving for r is very straightforward, to add, divide, and then take the cube root. So 72 over 4 pi raised to the 1/3 power is equal to r. There's our critical point. Now, let's go back to step 6. And now we're going to have to test everything, or think about the domain. So how big could the radius be? Well, I have a problem, because if the radius is 0, it's never going to be equal to 36. So we certainly know that 0 has to be less than r. And although I think it's a pretty janky way of thinking about things, as the height goes closer and closer and closer to 0, the radius would have to get bigger and bigger and bigger so that we have 36 square inches. And so while I'm not really in love with it, I will write that it is less than infinity, but we should know that because everything is less than infinity. So we're testing a couple things here. We're testing this value. We're going to test 0, and we're going to test infinity in what? In our original equation, to see which one optimizes our solution. And I think that you should see what's about to happen here. So we're going, let's take a limit as r goes to 0 of 2 pi r squared plus 72 over r. And sure, that piece is going to go to 0, but this piece is going to go to infinity. And now we have an infinite surface area, and that is not minimizing anything now, is it? Let's keep going. If I say the limit as r tends to infinity of my 2 pi r squared plus 72 over r. Now this piece goes to 0 as we go to infinity, but that's going to go to infinity, and so sure. Our final value is right here. We'll plug in the surface area of 72 over 4 pi raised to the 1/3. This is certainly going to be some numerical value. I could punch it in, I could get it for us, but it's the only thing that's going to get us a value, and we're done. We've found our optimal dimension for the radius. So r should equal 72 over 4 pi to the 1/3 power inches. What do we want, though? We want the optimal dimensions, and so I'm going to need the height as well. Can you see how we're going to get it? Oh, right here from our constraint equation. And so, not that I want to do any simplification, and I'm not going to. H will equal 36 over pi times, and check this out, 72 over 4 pi raised to what power when I square something that's being raised to the cube root? To the 2/3 power. I need to remain the units as inches, and we're out.